Yeah, we'll wait for a couple of more minutes before I start. Okay. Okay, so we have most of the usual attendees. So I will start. Sharing my screen. Okay, so you can see my screen and you can hear me as well, correct? So you can hear me? Hello, can you hear me?
Yes.
Okay. Okay, so last time, yes, we saw, synchronous system modeling, and we were beginning to see asynchronous system. So let me summarize. Synchronous system is something where it's a paradigm of concurrency, where you have a notion of a global time, okay, and all events across different processes are synchronized with respect to that global time, okay, which is in terms of transition system parlance, where it is equivalent to at each step marching every the transition step of every process in the mix. Okay, so whereas in asynchronous system, there's no notion of time. There's only things that there are actions or events that happen, and there is some ordering of events. Either some events are ordered or some events are not, and the processes have to synchronize explicitly using synchronization primitives, or through by communicating through shared variables. Okay, so that is the notion there. So as an example, so I'll move to a synchronous system right away, since we have seen synchronous system. So for example, here we have three processes. Okay, these are sequential each of them is a sequential process, and the atomic actions here are the statements in each of these processes. Okay, so as I said, there's no notion of global time, and the behavior of the concurrent behavior of the composition and the asynchronous composition of this thing can have any interleavings of the individual actions in each of the process. Okay, yes. So another way to look at it is that any step of any one of these process can be scheduled at any one time. So therefore, here, as I said, the transition system for each individual process expresses the execution of one atomic action, which is in this case is the statement. Okay? And therefore, any interleaving of these atomic actions across these processes are included in the behavior of the asynchronous composition of these concurrent systems. And that's why here there is the statement that at the end of execution of all the statements in all the processes will yield the claim that it will yield x is equal to 11 and y is equal to 21 is not true, because you can see that there is an interleaving in which this end state is not necessarily true. For example, you can have this incrementation of thread 3 of y if it is scheduled before y is set to 20 in process 1. You can have a state in which y can be 20 and not y is equal to 21. Okay? So how do we, the question is, how do we symbolically construct transition system, define a transition system which represents the behaviors of an asynchronous composition of individual transition systems? And we saw that one way of doing that is to define the combined transition relation as follows. So the state includes the global state, which includes all the states of each of the individual processes. As I said, some of the individual, there's a part of the process which is common to all of the processes, which is the shared part, and then there are local component to each of these states, which is assumed to be modified only by the individual process, and therefore the global state consists of the local states of each of the processes and one copy of the shared component. And that's how it is constructed. And so the global state is S cross S, and each individual process can modify their local state or any of the shared component. And this behavior where you're yes, so the so in each step you're allowed to schedule exactly one of the process, but the process that you schedule can be arbitrary, and And that effect is exactly expressed by this disjunction. So each disjunct here correspond to the case where the process, one particular process is scheduled. So if that is scheduled, then, by the way, I'm sorry, each of these should have T1, okay? So TSS prime, T denotes the composition, the transition system of the asynchronous system. And there should be a T1 to Tn here on the right-hand side. So when if T1 is scheduled, then all the rest of the variables, corresponding to which are local to the other processes remain unchanged. Okay, so each disjunct here correspond to scheduling a particular process. So any one of these, so this includes all the behaviors that I talked about of scheduling individual processes. So there's no assumption about which process is to be scheduled next. All it says is you can pick one of the process and schedule that by executing the transition step corresponding to that process. As you can see, so there can be behaviors here which are usually kind of not don't happen in real. So it can choose to there can be an interleaving where only one of the process is continuously scheduled. Okay, so even that is a permitted behavior in this asynchronous composition. Okay. Yes. So now we'll have to see. So this is the overall way that you define the combined transition system given individual transition things. So it is just a disjunction, and it's a disjunction that gives you this non-determinism of that permitting to schedule any one of these processes. Okay. Yeah, so I'll take, rather than using this example, which is, you can model this, but so that's why in asynchronous case, you need to have explicit way of synchronizing these things in order to avoid such unpredictable and data races. So here, since we are not, so here all X, Y, both X and Y are part of the shared memory, and correct. And therefore, that's why, so there you get, and since any process can change any one of these things, and there is no synchronization among them, that's why you're getting these data races. So in an asynchronous system, you need to have some synchronization primitives to control the access to shared resources, in this case shared variables, so that your behavior will be predictable and as desired, regardless of the order in which the actions are scheduled among the processes. Okay, so we'll see an example which is a little bit more interesting, which which implements a way of controlling access to a shared variable. Okay. So here's an example. So here there are two processes. They're identical in terms of their behavior. So there are two sequential processes which are intended to be composed asynchronously. And each process starts with an entry point, PZ, L0, entry point location L0, and goes to NC0. Okay, so the idea here is to design these process, which when asynchronously composed, allows only one of these processes, I mean, at most one of the processes to be at the critical section CR0, at location CR0, where the shared resource, which in this case, the shared variable turn, is modified, okay? So that is the goal here, okay? So we, and in order to ensure that, what we do is in both, and yes, both processes, they just, go through an infinite loop, circulating between L0 and going to the non-critical location NC and then making a move to the critical location, and this and here you see there is a synchronization primitive that we are using to block entry in a constrained way. So wait is a construct that implements a busy wait. Okay, it allows a process to go to the next location. It forces the process to wait until this Boolean expression, which is an argument to wait, becomes true. Okay, so when it is false, it makes the process wait at the same location. Okay, so here we are making process P0 wait on the value turn is equal to 0. If people have programmed concurrently and you have come across the notion of a semaphore, that is what this turn is like. So, two process one simplest way of having two processes synchronize with each other is to use a Boolean variable called a semaphore, and one process waits on the semaphore being, which in this case is turn, being false, and the other one enters the critical section only when it is 1. So here, process 0 waits until the semaphore turn becomes 0, and then it goes into the critical section, and immediately it sets the semaphore to 1 to allow the other process now a potential access to the critical section. Because turn, the other process waits, for turn becoming 1. Because turn can only take two values, 0 or 1. You can see that, this, enforces the requirement that only one of them can be, at most, one of them can be at their corresponding critical section location, which is CRI. Okay, so that's the informal description here. So that is the intent. Is that clear from the informal understanding of this process? Yeah, is that clear? Yeah, so each process, now this is the process is assumed to be modeled. The transition system for the individual process is, since it's a sequential process, it can be modeled in the way that we saw earlier. Okay, so which consists of, which describes what action to be taken when the that particular process is at one of the three locations that are that are possible: P0, NC0, and CR0. Okay, so if it is at, so this is parameterized with respect to I can be either 0 or 1. Okay, and so they describe process P0 and P1, and if PC is at Li, which is L0, then you unconditionally go to NC, to the non-critical location, and nothing, without changing anything else. And if you are in a non-critical location, then if turn is 0, is I, then you wait until turn gets the value I. Okay, if it is I, then you move to your critical section. Okay, if it is not, then you stay. If it's not, as you can see in the here in the last but one disjunct, if you're at NCI and if turn is not I, then you stay busy wait and you stay at non-critical, the NC location, non-critical location. If it is I plus 1 mod 2, okay, that is it's different than I, then you move into the critical section. So since this is an infinite loop, you never reach L0 prime, okay, and that's what the final disjunct is saying, okay. So if you're at Li, you will move to Li prime only when false is true, okay, which means that that indicates that this is an infinite loop. Okay, so the question is: so the initial state is, we assume that the turn variable is initialized to some arbitrary Boolean value, either 1 or 0, and each process is at their entry point location, L0 and L1 respectively. So given this, we want to ensure two things. Okay, one, I've already told you that, which is a safety property, that we want to ensure that P0 and P1 must not be in their respective critical section location at the same time. Okay, and that's what is enforced by this semaphore. And we also want another property, which is usually called a starvation freedom property. We want each process to be not starved, that each process to be not denied access to its critical section indefinitely. Okay, that is, you want each process to be at its critical section, infinitely often. Okay, so we will see. We will first construct a symbolic transition system for an asynchronous composition of P0 and P1, as per the general scheme I showed you earlier, I defined earlier, and then we'll see if these two properties are indeed, indeed true. Okay, so I hope you're at least convinced that the safety property, which says that at most one of the processes should be in this critical section, is true. Okay? Or is based on my informal description that I gave. Is there anyone who believes that, who is not convinced that the safety property as stated here is not true for the concurrent composition of these two processes? Is everyone convinced that the safety property is true? Say yes or no. Hello? Is everyone there?
Yeah, I think it's.
Okay. So if there are no questions, then I will move on.
So what about starvation?
Yeah, what do you think?
It does not hold true, right?
Why do you think it does not hold good?
I mean, when suppose in the first process enters in the critical region, then turn becomes one. So second, so uh, wait. Okay, okay. I understood. No problem.
Okay, so it appears that it is giving the other process a chance. Okay, and like you said, so because the first process sets the turn once it leaves the critical section to 1, then the next time, certainly it cannot enter in an obvious fashion. Okay, because turn is not again 0. It has to wait on turn becoming 0. So, and that is possible only if P1 is set to 0, which can happen only if the other process enters the critical section. So it, on the face of it, it appears that this starvation freedom property should also hold good. But we will look at the asynchronous composition a little bit more carefully. And
So I'm just verifying. Safety property is not true, right? They both can be in the critical
no,
section.
they cannot. How can they be? I mean, informally, I'm saying because so if
Suppose the first process is in the critical region, so turn becomes one, and then the next process, which is in the not
no. I'm saying that the initial state is you start with either turn be 0 or 1, and both start at P0. Okay, I mean at their entry point, I mean L0 or L1.
yeah.
Then if turn is initially 0, then this only process 0 can enter to the critical section.
Yeah.
Okay?
Then turn becomes one, so the second process, the wait clears off and it enters the critical section, right?
Yeah, the turn becomes 1.
So both of them are in critical region now.
No, how? No.
First
Where?
one leaves critical region when its turn becomes 1, right?
My first one is 1?
I mean, when the critical region 0 gets executed, it then leaves the critical section, right?
Okay.
Yeah,
Yes.
that's right.
Okay.
Okay. So these things will be clear. That's why, see, this is what indicates that, especially when you're moving to concurrent systems, these things can become quite hairy So, this is one of the simplest protocols, mutual exclusion protocol that exists. Okay, so even there, it can be somewhat challenging to ascertain that you indeed these properties can be true. So that's why there is the need, the importance of doing something like a formal check becomes significant. Okay, so let me move on. So here is the first line here, okay? It's an instantiation of the general rule for asynchronous composition that I, so that I've shown. So what I've said is the initial state is defined, with PC0 and PC1 being the respective entry points. Turn can be anything, okay? And yes, so the transition, this is the first line, is the transition system for the synchronous composition. All it says is that you either schedule the first a transition from the first process, in which case you hold PC1 at the same point, or you schedule the second process, process 1, and you hold the first process. Okay, so either one is what is possible. Okay, so yes, so constructing the asynchronous composition is very simple. Okay, so to analyzing it is can be challenging. So that's what. So if you based on this symbolic representation, if you were to construct show the representation of the combined transition system as a transition graph, okay, here's what it would look like. Okay, so ignore the first two states. I have, this is wrong, so assume that you're starting with the initial arrow is to the second, okay, state. Okay, ignore the first one. So either of these two, turn 0 and turn 1 with L0, L1, L0, L1, is the initial state. And from there, either of them, can go to NC1. I mean, the non-critical location, right? And after that, obviously turn, you could, yes, see, there is a self loop here. So since turn is 0, yeah, turn is 0, NC1, if you're at NC1, obviously that cannot proceed into the critical section. That's why it is, busy waiting here, correct? Yeah, so the first process is still at L0, okay? And the second process has moved to the non-critical section. And process 1 can move to critical section only when turn is 1, and that's why this is here. So if the first process 0 moves to its critical section, of course, it can, NC0, then it can move into, so it can either directly move to its critical section if P0 happens to be the next scheduled process. Otherwise, you can also have, there is a possibility that that is not the next scheduled one. And if process 1 is scheduled, then you will have a state in which both of them are in NC0 and NC1. Okay. And yeah, so here also there is a self loop. Why do you think there is a self loop here? So here is a situation where turn is 0, and both of them are at NC0. I mean, in their respective NC location. So you would think that it has to move to P0 has to move to CR0, isn't it? So why?
I mean, so if both of them are at the NC locations, then one of them is waiting, and so that is representing the waiting process.
No, but yeah, why should, that happens when, although the NC P0 is ready to move into CR0, the scheduler stupidly never schedules process 0, okay? And it chooses to schedule process 1, which is certainly possible because we are saying, you know, in asynchronous composition, we are including every possible behavior of interleaving these actions. So we will be, you know, we'll have to, yeah, so this includes, this is a case where the enabled process is not being scheduled, okay? So here you know that NC1, process P1, cannot, you know, make progress, okay? Because it can do so only if turn is 1. But yet, it is quite possible that P1 continues to be scheduled, okay? So that's also a possibility, okay? Because asynchronous, you know, the way we have defined non-determinism is a non-determinism, you know, we use this, it can be, we are ignoring the, any schedule is possible. And it's that
causes starvation, right?
that is exactly right, okay? So this includes behaviors which realistically may not be, you know, may not be possible you know, in actual system. But since we are throwing away, you know, completely abstracting the scheduler, and we want to analyze it without, you know, in the arbitrary case where any schedule is any possible, that's why you're saying, yeah, so if it, so this does include behaviors which can ignore an enabled process. By enabled process, I mean a process that can indeed make progress forever, indefinitely, okay? So that is included as one of the possible behaviors as a result of the way that we have completely used non-determinism to include all possible schedule. And that's precisely the reason why it has certain behaviors, certain paths on which a particular process can be denied access to critical section, okay? So here I am only shown that part of the state space, the combined state space, which are reachable. And as you can see, the state in which both processes are simultaneously in their critical location, that is CR0 and CR1, is not reachable, okay? You know, and of course, a complete transition system would have to have CR0 and CR1, but that would not be reachable from our initial state. But you can have transitions from those unreachable part into these reachable part, okay? But that is not, you know, harmful. But, you know, so by virtue of the construction of this explicit transition system graph, we have kind of ascertained that the safety property is true. And we have also seen that there are paths here in which starvation freedom is violated, okay? So that, yeah, so, you know, so that we have already answered. That's, so system is indeed safe, okay? And, you know, starvation freedom is not. But it could be if, yeah, so see, this is the consequence of kind of abstracting away the scheduler. So we don't want, we want to be able to, you know, reason about these systems in, you know, for arbitrary schedule. But what will happen is, you know, especially properties of the kind you will have to, these are called liveness properties, that eventually something good happens, okay, will become, by virtue of the fact that you're including all possible schedules, will be not true, okay? So sometimes you want to do this check, define model checking, for only a subset of the paths, that are included in the non-deterministic abstraction. So which are, which are called fair paths, okay? So there's a notion of fairness that we will introduce, okay? And this becomes critical whenever that you're using a determinism to represent concurrency. This is a undesirable consequence, okay? So there is this, we need the notion of fairness. So I'm introducing these things informally, right now, so that you'll be able to start using new SMV and so on. We will be revisiting, these things, how you specify this, how you specify fairness constants in a more formal way once starting next class, once we introduce the temporal logics, okay? So here, how do we avoid? Yeah, so what are fairness constraints? So the way that you can avoid this pitfall of abstraction, okay? So this is the consequence of over approximation, as they call it. This abstraction is including those behaviors that are, usually not desirable. So, and the way that you do is by specifying what are called fairness constraints. So, in addition to the Kripke structure, so fairness, the usual Kripke structure that you have, before you model check properties, you will have to, specify some fairness constraints as well in order for model checking to be useful, to be practical in some cases. And this is an informal definition of fairness. So normally model checking means you have to verify the given property for all possible behaviors as we defined the behavior for in terms of Kripke structures. But we will restrict it to only fair paths in some cases, okay? Model checking in the presence of fairness, what it means is, that the desired property should be true only for fair paths. A path pi in M is called fair if along pi certain events, specified events must occur infinitely many often. Okay? That's how fairness is specified. Okay? Certain events or sequence of events have to happen infinitely many times along the path. Okay, that's when it is considered as a fair path. Okay, so let me go back to okay. So in this case, do we want to, if obviously this starvation freedom is not true for all paths. So if we restrict ourselves to those paths in which in every state, those paths, such that in every state on those paths, an enabled transition corresponding to a process is not ignored indefinitely. Or a reverse way of stating it is, in every state, enabled transition corresponding to a process must happen infinitely often. Okay? So a process in any state has to be scheduled, cannot be ignored infinitely often. If that's your fairness, in the way that you restrict defining fairness, then obviously the paths in which you starve a particular process, which are the paths where you keep taking these self loops here, okay, infinitely often, forever, will be avoided. And as you will see that when you use new SMV, especially when you want to prove these kinds of liveness properties, you have to specify some fairness. Otherwise, generally, when you take the asynchronous composition, those properties will never be true. Okay, so I want to end in this my part today. Addressing one question. This kind of briefly came up. Somebody posed it last time. Okay? this was about something, that there'll be an explosion. Okay, you'll have to take, if it is S cross S, you will have to, cross product of all the individual states. The state will be too huge, correct? So that is that is true. See, as we move along, we will see. So we've already talked about SAT solving. SAT solving is an NP-complete problem, a classic NP-complete problem. Model checking is harder than NP, okay? And we will see, although in this course, we will not be getting very deep into complexity issues of model checking. As we go along, as I introduce those algorithms, I will be talking briefly about its complexity. So model checking is indeed P-space complete class, okay? Which is harder than NP, but less, not as hard as exponential time. Okay? So that's the worst case complexity of model checking for finite state systems. But here what I'm talking about, so it is already bad enough, okay? And the parameter over which it is P-space complete, usually the parameter that is used is the number of states and the size of the formula that you will verify, the temporal logic formula. These are the two parameters, okay? With respect to which it is P-space hard, okay? So, but it's also sometimes, although in the worst case complexity is that sometimes the reachable set it might be a small one, and therefore it can be. So it also depends on the reachable set of states. Having said that, even before you do the model checking, so here when you compose concurrent systems, it's already, because you're taking the cross product, your universe, the size of the universe of states is already exponential in the number of process components, correct? So in the worst case, so your reachable set of states could be exponential in the number of process components. So even just representing your problem can blow up, let alone, for now, ignoring the complexity of the thing, of the model checking problem. This is what is called the state explosion problem, okay? So in real life, when you have, and especially with concurrent systems, that is true, even when you compose sequential program, so you will have to deal, this problem of state explosion will have to be dealt with in a different way, okay? And that is where modeling and compact representations of your transition system, how you partition them, all that becomes important in a practical sense, okay? That's the point that I want to bring out. When people talk about state explosion problem in model checking, this is what they mean, not the worst case complexity of the model checking problem, the class to which it belongs. What you talk about, what you do is this, the state that you will have to deal with it. Now, see, synchronous, okay, so that is the, universal state is obviously exponential. So you will have to, and the one hope that you might have is, okay, I mean, two ways of dealing. One, maybe the reachable set of states is small, okay? Still, maybe then it will succeed. But that is where symbolic model checking, gives the breakthrough that was needed. If you do explicit state model checking where you manipulate, your algorithm tries to construct the transition graph, then you're pretty much doomed, okay? Whereas if you represent your states as symbolic formulas, you can, in a lot of cases, get an exponential compactness in the way that you, in representing the states, because these formulas represent sets of states. And sometimes, even though the universe of states can be different, the set of reachable states may have compact representation, in symbolic representations. And your manipulation of formulas might still be manageable in terms of giving you, results in practice. Okay, so we rely on those two things and various other techniques where you use very clever abstraction to throw away irrelevant part of your which is not reachable. Okay, so the reachable set, you see, in synchronous system, because of the lockstep composition that you use, and there is no non-determinism there. So because every state makes a transition and they modify their own parts, except for some inputs from one system being fed to the other. So asynchronous systems, because they'll have to consider all possible interleavings there, and for every possible interleavings of all the actions in the different processes, and you can see that depending upon the, as we increase the number of steps, these interleavings can grow exponentially in the number of actions across processes. And each interleaving can potentially give you a different, in the worst case, a different reachable state. And therefore, this makes a synchronous system even harder to verify, because of the fact that you have to consider all possible interleavings. Okay, so this is something that I wanted to mention. So all research since the early days of model checking, especially now, are in advances in tackling this state explosion problem in very different in different ways. We will in this course, after introducing the basic algorithms for temporal logic model checking, we will look at some mature, established ways how to deal with this state explosion problem. Okay, as towards the end of this course. Okay, so do I have anything? No, this is the. I guess this is the last slide that I have. So what from here on, Zubin takes over. Okay, and he will show the two examples. He'll introduce a new SMV, and I've asked him to use the same two examples, one synchronous and the asynchronous example that you have seen, so that he'll be able to, you're already familiar with the example. So I will hand over the baton to Zubin, unless you have some questions on this part. Zubin, I will make you.
Yeah, I can't screen share right now.
Yeah, I'll just one moment. Do you have any questions? No. Okay, Zubin, you are now a co-host. You should be able to share your screen. Sorry,
Okay,
yeah.
Is my screen visible now?
It's visible, but you could make your possible
font size.
Font size bigger, at least for my eyes. Yeah, this is good. So does everyone see Zubin's screen? Yeah, I'm assuming yes. Yeah.
Okay, so we're going to look at new SMV, which is a symbolic model checker. So you can define finite state machines and transition systems and symbolically execute them and verify properties about them. So the first construct you need to know about is the concept of modules in NuSMV. A module is basically a collection of variables. So uh, a module can have Boolean variables. A module can have var. I can have a Boolean variable b. I can have so this basically defines or these variables basically define the state space of your finite state machine. You can have uh, any custom kind of set. Let's say state is uh, so in the example of mutual exclusion, you would have something like non-critical state, critical, uh, non-critical, waiting, critical, and exit, something like this. So state can be any one of these values. So this is how you define any custom kind of state values, and your overall state will be a product of all these vars that you have in your module. So you need a main module, which is the one that will be symbolically executed. So let's look at the example we discussed in Professor Shiva's discussed in class, which is this one. So a 4 counter. So a 4 counter has 2 bits of state, another bit to represent the input, which can be 0 or 1, and it can also reset back to 0 at any given time. So uh, we can model a counter with 2 Boolean vars for the low bit and the high bit, and we also uh, mentioned that there are 2 I vars or input variables for uh, any possible input and whether we're resetting the state. So the way we express transitions in the system is we start an assign block under our module, and in the assign block uh, we can describe the initial value of a particular variable. So the initial value of low is
But
false. We
I
can
just
also
make
assign
one comment here. I think your counter is slightly different. I think I had only one input, which was the reset input. Okay, you have two inputs, input and reset.
No, but there's also this, right? There's also this, right?
Yeah, but that's a different process.
This is for the input, right?
Yeah,
Whether
but
you
that's the reset input in my case. Okay. That's all. There's no two input.
sorry.
That's the reset input. But anyway, why don't you describe your system? So so that should be fine. Okay, even if it's different, that's okay because that's
Okay.
for illustration purpose. I don't have two inputs. I have only one input.
No. Okay, yeah.
Yeah, okay. No,
So
that's fine.
one input is the input is to decide to whether to increment the counter or not. So if you set the input to 0, then it will not increment the counter. If you set the input to 1, it will increment the counter.
Okay.
And if you reset at any point, it will go back to 0. So the way we model this is that
Okay, fine. Yeah,
uh,
so you have two inputs. Fine. Yeah.
yeah, we have 2 inputs. So for the initial state, we can give a single state or we can give a set of states. Right now, we only have a single state, which is false. And for the next state, first we check if the reset counter is not set. If it is set, we this and directly short circuits and we get a 0 here. But otherwise, if reset is not set, um, the low value is low XOR input, which is XOR is basically addition modulo 2. So we increment low, and similarly for high, the initial value of high we start at false, and then to go to the next value we check that reset is not set, and if that is the case, then we uh, add the carry bit from the low here. So the carry bit for the low will be low and input. If low and input is both 1, then we need to add 1 to high. So let's execute this model in new assembly. So if you just want to check the syntax, and later when you add specifications, we haven't added any specifications for this model yet, but if you execute new assembly in batch mode, it'll check the syntax, and this command executed successfully. So there were no syntax errors, and whatever specifications we defined, which we didn't define, if there were any specifications that we defined, then it would check those also. The other way to use new SMV is to use it in interactive mode. So to use it in interactive mode, you pass it this -int flag while loading your file, and uh, so now you're in the interactive mode of new SMV, and the first thing we need to do is uh, write the go command to initialize our module state. So new SMV has the command line has a useful help command also, so you can use help some command to see exactly what it does and see what flags it accepts and things like that. So the go command initializes the system. Now, what we need to do now is to pick an initial state. We do that by using the pick state command, and the I flag is taken care of. So it tells us that there is only one state, which is setting low and high to false, and we can proceed. So if there were multiple initial states, we could have picked one of those states. Uh, Now the other useful command is simulate, and simulate takes a bunch of flags. So we can simulate it on random for the model for randomly for some number of steps. You can simulate it interactively, and there are a bunch of commands to uh, control the output of simulate. So uh, you want to show all the state variables even if they don't change. That's why we pass the a parameter, and we want to do it interactively, and we want to simulate it for say 10 steps. So uh, our initial state was false comma false. Now when we simulate it, we get all the possible available states. So uh, if we set our input to true and keep the reset as false, we can then jump to this state where low is true and high is false, which is the one state. And in any other case, where if we set the input to false or we set reset to true, uh, then we jump back to the initial state.
Yeah.
So
So
let's jump to
Naveen,
this
the
state.
inputs here are being picked by the simulator itself, is it? Or are you,
Yeah. So it's giving us four options. So it's giving us options to choose both input and reset. So we can choose input as true and reset as false, or input as false and reset in true, and so on. So we have four examples. Four possibilities. We'll choose the first one, which is 0, which is setting input to true. Uh, if we choose that, the program has advanced to this state, and now the next state we have, if we keep our input to true, is the true false state, which is the 2 state. The other possible states we have is we can go back to the beginning. If we set reset to true, we can go back to the initial state, and if we don't set either input or reset to true, then we just stay at the current state. So this is the current state, and this is the next state we'll jump to if we select 0. So now we've advanced to the next state, and we are in the true comma false state. So if we do nothing at this point, we'll stay in the true comma false state. But if we set input to true again, and reset to false. We'll jump to the true comma true state, and we can do that by selecting 3. And now whatever, now if we set either reset to true or input to true, then we end up back in the initial state, because either we reset or our counter overflows. So we can do that, or we
May I
can
ask
stay
a
in
question?
this. Yeah.
Uh, where in a program you specified that if reset is for true, then the values are resetted?
Yeah, so over here I'm checking if not reset. So if reset is ever set, is sorry, uh,
Okay,
yeah.
got it, got it,
So
got it, got it. Yeah.
uh, if both low and high bits are set to false, if reset is true, right? Because it's not reset and that.
Okay. I did not pay attention. Okay, thanks.
So we can just jump in and
So,
so
Zubin,
now
what
we finished our
happens,
execution.
yeah.
Yeah.
What happens if you start from an arbitrary state? With simulator, it'll ask you to pick one of the initial states.
Uh,
Suppose you start from,
so there is only one possible initial state,
here
because
it is like
both
that.
the variables are set, but we can give it.
Suppose it's true. I mean, suppose
Sorry, I can't hear you.
maybe you don't, suppose you want to say initial state is arbitrary. Can you specify that? I think you should
Okay,
be.
so yeah, we can either, yeah, we can either uh, we can either give a set of possible initial states, so we can say low can be false or true, or we can simply remove this init statement, so it'll automatically take it to be any one
What
of the
happens if you
permissible
remain
states.
in its state? Will it still simulate or it'll
Sorry,
force?
I could not.
Huh?
So I could not hear you. Sorry.
No, no. What happens
Can you
then
repeat?
when you, in such a case where you have not specified the, I mean, the initial state is an arbitrary state, how does the simulate command behave?
Yeah.
Illustrate that.
So
But you have to pick a state,
so
seems like.
to pick state, you have to pass the -r or -i parameters. So if you pass -i, then you get a list of all possible states, or it can pick a random state for you.
Yeah.
So right now I remove the init statement, so all possible states are
Yeah,
available
that's all.
to
So
us.
it give you the all possible options. So you'll have to pick one
Yeah.
for it to
Yeah.
march. It won't print out symbolic representations.
No,
of
it won't. It'll pick out, or it'll print out all possible options.
Yeah. So it is not doing symbolic execution the way I had illustrated in the class, but it does simulation. Okay. Yeah.
So big state is essentially picking the first state, is it? Like
This is how you
starting
can
state.
use new SMV to symbolically to
You had a
execute your
question.
models. So
There was a question. Can you repeat the question?
Yeah.
sorry,
Yeah. So
I can't hear you.
hello. Can you hear me? Hello.
Yes, I can hear you. Zubin, can you hear me?
Yeah.
I'm sorry. There's like a lot of thunder
I
on
can
my
hear
end.
you.
So the pick state command, does this basically pick an initial state for the simulate command to work on? Like, is that all the pick state command is doing? Hello?
Zubin is
Yeah,
hearing
it
you.
picks an initial state for our simulation.
Okay.
Yeah,
Yeah. So
It's-
among the possible initial
it
states,
just picks an initial state for us.
it'll allow you to pick an initial state.
Yeah.
Right. So this is just picking the initial state for the simulate command to
Okay.
work on.
Correct. This is not model checking.
Yeah.
Yeah. So we can also model it this way. So this is the same thing but modeled in a slightly different way. So instead of using booleans, we use explicit was 0, 1, 2, 3 states. So the state can be 0, 1, 2, 3, input can be 0 to 1, reset can be no or yes. So basically booleans, but we give them different names. And you can write our model like this. So our initial state is 0, and the next state, if reset is yes, is 0. If input is 0, then it is the same state that we started with. Otherwise, if input is 1, we just advance the state. 0 becomes 1, 1 becomes 2, 2 becomes 3, and 3 becomes 0. And again, our initial. So in this model, we're not designating the input and reset variables to be input variables specifically. Sometimes this might be useful because um, uh, a new SMV does not allow you to use input variables in many places. So sometimes you might want to write a formula mentioning input variables, but new SMV won't allow you to do that. So you can work around that by making them normal variables and then having uh, no constraints on their transitions. So initially input can be either 0 or 1, and uh, at every state input can change arbitrarily, and the same with reset. uh, Reset can be either no or yes, and the next state of reset can also be either no or yes. So we can try to yeah. So
Yeah, I just wanted to add, Zubin, I wanted to add the comment. So the way that you just now showed is the way that I modeled in the class, where the input is included as part of the state. Okay. Okay. So you will have, yeah, 10. I mean, I will go beyond 4:45. So you have to move on. I mean, now you can show next time also. You go at your pace.
Yeah.
Okay. So we can also.
Why the state 1 and 3 is the same and some are not displayed?
Because it only displays the changes. So
Okay.
so this is the only the changes from the previous state. So
Acha.
so these are the same except input has changed from 1 to 0 and so on. So this is one way to model it. So this is another possibility when you're modeling things. But okay, so now let's look at let's complete this example. So uh, we're composing two transition systems. So the counter transition system is the one that I've already defined here, and uh, yeah. So counter I've defined, and I'll add the init statements back again. Yeah. So uh, so this is one module. So we can refer to other modules as parts of our main module. So in our main module we have a C, which is a counter, and now we define another transition system, restrict. And restrict takes a single input, which is a reset, which is a boolean variable. And transitions in restrict uh, are only true if reset is false. So this trans constraint, so trans can be any boolean formula. So it can be something like low and high, and it can also mention the next thing. So it can relate to states in your automata. So it can be something like low and next high, which means that low is true in this step and high is true in the next step. So what this means is that the only transitions that will be allowed to take will be the ones that satisfy this relation. So uh, for a restrict transition system, the relation is very simple, simply that not reset. So um, this takes reset as an input so that we can tie together the reset of this counter and restrict, because right now they're both independent, but in main we can uh, have a var r which is a restrict parameterized by the reset field of our counter module. So this reset will be the one passed to this restrict, and this denotes a synchronous composition of these two transitions. So both C and R will move in lockstep. So this has the effect of not allowing any reset states. So um, we can model this again. So
where have you specified that it's a synchronous composition?
so by default it's synchronous.
Okay.
So if you just mention it as this, it's synchronous.
Okay.
But if you want it to be asynchronous, which we'll take a look at in a while, you have to
Okay.
write
You have to
process.
explicitly say it. Okay, fine.
You have to say this is a process, so it's asynchronous. So uh, we need to pick an initial state. So there's only one initial state. So we picked that state. Now we can simulate AI, stimulate for 8 steps. So now you see that we are not allowed to take any transitions which set reset to true, because uh, restrict uh, has this as a transition condition. So uh, now we can only set input to true or input to false, and we have no freedom in deciding reset. So we can again go through this. Uh, Transition. So show traces will show. Uh, oh, sorry. Yeah. So this is cycling through all the possible things. Show traces will show trace of the simulation which is ran. So we go from false to uh, yeah. So this is how show trace works, and this is how we can compose things synchronously. So we can so the last thing is we can we can give some specifications about how our modules how our automata are supposed to behave. So in linear temporal logic we have two very common operators, G and F. G says that something will always be true. So G of P means P is always true. It's at every always P is true. At every step of our transition, some property has to hold. And F says that eventually some property has to hold. So uh, this specification says that eventually we must reach zero. So eventually not of high and low, which means that both high and low must be false eventually. Uh, if you add a G before that, this means that always eventually high and low. So no matter where we are, eventually we'll reach a zero state. So if we try to
This you have used an OR there. That is
not a for.
Okay.
So both have to be false.
Yeah.
So we can check this using the batch mode. So and it says that this property is false. So it gives us a counter example. We start with 0, we set input to 1, and we advance to our next state. Uh, Low equals true. Then we set, so this property is eventually false because input can always be false. So if we keep setting input to false, we'll be stuck at a non-zero state, which is true comma which is 0 comma 1 or 1 comma 0 whatever the one state, and if we keep input as false, we'll keep looping around and we'll never reach zero. uh, but we can specify some fairness conditions, such as, so a fairness condition has to be true infinitely often amongst our path. So it's not that it has to be true at all points, but it has to be true infinitely often as we in our trace. So in our infinite trace. So if you specify that input, uh, if we specify input as a fairness condition, that input will eventually be true, will be true infinitely often, uh, then we can indeed verify this property, uh, and new SMV verifies that this property is indeed true. So always we can reach a zero state. Always we'll eventually reach a zero state. So uh, I think this is enough for this time, and we can do asynchronous next time.
Okay. Yeah. Yeah, I think so. I think
Yeah.
so we can
Any
start.
questions about this so far?
Yeah. So when you're so you're saying var c is of type counted over there, right?
Yeah, yeah,
So essentially every module is defining like something which is some states and some relations
yeah,
built into it,
yeah.
and you can include it into other modules and all of that,
Yes,
right?
yes, yeah. So you
So
can
when
compose. Yeah.
yeah, so when you're passing this reset variable, what are you doing? Are you like passing a reference to
The
like
reset of the reset variable of this C.
right? I see. Okay, and then
So yeah,
yeah, and then it is interpreted to be, then all the transition relations of the restrict module is interpreted to be on the c dot reset.
yeah, yeah.
I see.
So I'll just show you the. So this is the example for mutual exclusion. So like I said, we're using process over here, so because it's, so we'll discuss this next time.
Yeah, but I think if you introduce that and we load the thing, maybe they could be simulating this thing. So that would be a good thing.
Which one?
For next time,
Yeah. Okay. Yeah.
maybe you can upload this thing so they can then upload and simulate. Okay, and then
Yeah.
you can explain the whole thing. Yeah,
Okay.
next time. So we will upload. I mean, Zublin will upload his example. So you could download new SMV and I mean USMV. How do you down? I mean, you just
So
Google search for new SMV. Is it?
yeah, the binary is available, I think.
Okay.
I mean, it'll be in your package manager also if you use Linux, I think. But, uh, yeah, you can download the binaries from newsmv.fbk.eu. You do need to apparently give your information and stuff, but I think if you're using Linux, you can get it through your package manager and you don't need to do this stuff.
There is a do not register.
I think that's it. We'll meet next time and discuss asynchronous
We will guys
process.
do download and then maybe you could simulate some things and then so Zublin will complete the example next time. Yeah.
Yeah. Okay.
Okay. Thank you. Thanks, Zubin.